All right, guys, we're back. It's Game 2005 in the fall 2018 semester at George Brown. That's game physics. And we're lesson 5, part 1 of our broadcast, even though week 6, right? So remember last week we had our tests. Lesson 5 fits in today. So again, just a couple of announcements for those people who are watching remote. Assignment 2 has been released. Please start that. Maybe if you want to pick your the same teams or different teams, it's totally fine. I'm okay with that as long as you mention your partner's names again, like before. There's only 3 questions this time. I had 4 questions last time. These questions are a little longer. The assignment's still worth 15%. This assignment number 2. Just wanted to mention that. However, the test, which is going to happen on week 11, so that's 5 short weeks from now, is going to be worth 20%. So that's going to up the game in terms of how you do. And we'll talk about the test a little bit later on. I won't record it just because I want to talk about this stuff on the recording. But I think for the most part, I think we did well as a class and better than last year in general. So last year we had about an average 10% lower class-wide than this year. So that's good. All right. This year's? Yeah. This year's average was 74.6, something like that. I think it's pretty good. I think it's a good average for a class. I've had mixed results with the math and physics in the past. Typically, like I said, if it's higher than 70, I think I'm good. I'm happy. 65 is a tough test. That would be a tougher test. And anything lower than 65, then I got to really identify maybe something didn't go right, or we didn't, study properly, or I didn't talk about things right, or something. But typically, that's where I want to stay, 65 and up. 75 is really great, and I'll talk about the results later on in more detail. All right. So today we want to talk about motion in 2 directions. Last time we talked about motion in 1 direction, and this just extends that stuff. So anything we talk about today is just an extension of motion in 1 direction. So I'm going to grab the lights. And what I mean by extends it is some of the same formulas, of course, the last one. Some of the same formula that we used we saw in the first one, which was on lesson 4. They're just going to be extended to both, kind of a 2-axis. When I say 2 dimensions, 1 dimension means 1 axis. 2 dimension is 2 across 2 axes, right? And when it comes to 2 or more dimensions, you can use the same strategy and just add another axis, right? All right, so we talked about speed and the difference between speed and just a review a little bit. The difference between speed and velocity. So again, speed is, the distance traveled, right, per unit time. And velocity is an object speed and direction of motion. Velocity is in a vector format. Speed is more of a total number, right? A scalar, if you will. Acceleration, again, the change in velocity over a certain time. And gravity tends to pull things down to the earth, right? Usually gravitational acceleration is a lot of times in the direction is negative. We talk about gravity being, kind of going down. Down would be negative. Up in the up direction would be positive. So we talked about those things the last time. All right, so we talked about, stuff being thrown down. Let's say we had Galileo. He was this guy. He was talking about things falling down, right? And he would just, throw things down from a building, right? And then when they fell down, they fell straight down, right? And you see that in this case, if you look at the marble or the particle, because remember we talked about also we're going to be dealing with particles to describe bodies of motion. You can see that the particle continues to accelerate in a one-dimensional path all the way down, and you can see the grid lines kind of describe when the next position is going to be for the particle. Now we can do this in code as well and simulate this. If we were going to simulate this in code, and again, maybe later on this week when I release the template, or next week, we'll talk about how to do this. But But think about this, even if you have a horizontal component, so this is just a vertical component, just y, right? So it drops. Whereas there's a horizontal component here and a vertical component. So notice that here, the marble, in this particular case, is at the exact same vertical component as the one-dimensional motion, right? So vertically, it's in the exact same spot on the bottom of the grid line here. Horizontally, there's another component on the x-axis now that pushes us out horizontally, right? But as you can see, it travels in what looks like an arc, right? And this is because of a couple of things, most likely gravity, right? The major factor here, as well as any kind of friction due to air or anything else that's that makes the marble fall a certain way. If this wasn't a marble and if it was something else like an air balloon, right, or if it was something like a little bit more wobbly like a water balloon, you might have a different motion described by the in this graph. But in this particular case, it's just a particle, and you can see that the difference is from one to the other. Okay, so when we talk about stuff, this is really weird. We have some new notation. So again, we have the position, and a lot of times you'll see this little mark on the top, which means it's a vector. So sometimes vectors can be described this way as well, not just like a line with an arrow, which is kind of interesting. So again, this is the displacement of the object is defined as the change in position, right? So just like it says that delta r, as an example, the displacement of the particle, right? Now we're just using another variable, but we always know that the change in displacement is the final displacement minus the initial displacement. And this is both on the x and y axis now compared to just one axis, okay? So the vector has two components. By the way, for the template that I'm going to be releasing this week, I'm going to be also including something called GLM. I don't know, does anyone know about the GLM library at all? It's actually the graphics library for the math library that I'm giving you guys, right? So you have the entire math library. You don't have to make your own vectors or anything like that when I give it to you. So if you want to do things like matrices or use vectors, addition, multiplication, dot product, cross product, all that stuff is going to be available to you in the template, right? So that way you don't have to make your own classes. I want to try and avoid doing those things as much as possible. Okay. Just like it says here, it doesn't matter 2 or 3 dimensions. The kinematic equations apply just like they did in the last lesson. The difference is that positive and negative signs aren't sufficient enough to determine the direction. We need more information, okay? Again, if you look at the average velocity can be thought about as the change in displacement over the change in time. So you have the displacement vector, and notice that again the vector has a little mark on the top, whereas the change in time does not. Time is something that consistently moves forward, and it's not a vector. Although we'd love to think that it is, right? If you're a science fiction fanatic like me. The instantaneous velocity is the limit of the average velocity as in delta time as we approach 0. And the great thing is about if you see these secant lines that the cross between kind of change in direction here, you can see that the change in displacement over change of time is kind of you get the instantaneous velocity, right, which is what we want to see. Okay, very similar to what we've seen before. And like it says here, the direction of the instantaneous velocity at any point in the particle's path is along a line tangent to the path at the point and direction of motion, which we're going to see in a second. And speed, of course, is a scalar quantity. So now we're looking at these equations again, and we're seeing vectors more than anything else. We have a vector quantity as opposed to just a value. And we're looking at like the average acceleration is the average velocity over the average time, velocity vector, which is, again, if you think about this, you can decompose or decouple the velocity to say that, well, if you want to find the average of anything or the change of anything, it's some final value minus some initial value, as long as, and these are all applicable with consistent velocity and acceleration. So if it's something that's really weird, it's really wacky, and it's not continuous, right? Then what ends up happening is these equations don't apply. We have to use another set of equations. However, for the game stuff that we're doing, you can assume that everything is continuous and nice, all right? Because we're gonna, for the most part, some of these equations that we're gonna see here, we're gonna fudge when it comes to actually doing stuff in programming. That's just the way it works, right? And like I talked about before, even the things like gravity and so on, we're going to set a value for gravity that makes sense for the game, not necessarily for real world simulation, right? So again, even though gravity is 9.81 meters per second squared on average, depending on different places on the Earth, it's slightly different as well. We'll probably be using a different value, and then we have to figure out how many pixels per meter in our game, or how many units per units per meter. So example, if you're doing in Unity, how many units per meter are in that particular thing? Or if you're making a web simulation, how many pixels per meter? Because once you have the pixels per meter, then you get a ratio that makes sense, right, in terms of motion. And that's what we're looking at. All right. So again here, you can see that a particle is going to start moving in a particular place, but there's two components now. We're going to have the velocity initial, and then here's the velocity final. You can see that there's two positions, but there's going to be a vector. So if this is the velocity initial, there's two components here. There's the x component as well as the y component. We're going to have to look both of those components in order for us to understand what the final velocity is going to be at some point in time, right? Does that make sense? So I know that it's just looking at position. Imagine this particle is moving in a particular path, and again, you have some kind of displacement from the origin here, where you have the initial displacement and then followed by the final displacement. Notice that the final displacement vector is farther, is longer. The magnitude of the vector is far longer, right? Why? Because you have a horizontal aspect, a horizontal component, the x component, that's pushing things further away, right? And you can simulate this by some kind of bullet or cannon, right? This is a typical example, by the way, we're going to talk about. You have a cannon, it's firing, and it's firing in an arc, right, as an example. And the cannon has two components. The cannon has an upwards component, and the cannon has a forwards or kind of horizontal component. And there's also, if you think about this, the up and down component, the vertical component, is being always reduced by gravity, always, right? On Earth anyway, right? And I'm reducing it frame over frame. So when I say frame over frame, whether it's seconds or frames, it's going to continue to reduce every single time until the bullet or the projectile hits the ground, right? Whatever that ground happens to be. So you can see here, the reason why it's going down in this natural motion is because it's being pulled down by gravity. Okay. I'm going to skip this one. And this one. And then I'm going to talk about two-dimensional motion with constant acceleration. We need to talk about constant acceleration because if it's something other than constant acceleration, like I said, our simple equations can't figure it out, right? So again, some of the equations that you're going to see are similar to the ones we saw in one-dimensional kinematics, but we're going to extend them on two axes. That's all it is, like we said before. Okay, so we see the now we're starting to use things like I's and J's. Okay, why I's and J's? Anyone know? Well, yeah, because math. Because math. So basically, you have some kind of x component, an x scalar and a y scalar, and you're multiplying it by I with a little hat on it and j with a little hat on it, right? And usually, if you want to put it in the third dimension, you put k. I, J, K, right? Those are the three dimensions that we're going to be usually talking about. And then, so you multiply, as an example, whatever I and J, the component of I and J is combined, to the on the x component of the scalar to get the final velocity. But if we ignore this for a second, we can say that the velocity on the x-axis, right, plus the velocity on the y-axis gives us the total change in displacement over time, right? So we see that there's going to be some kind of velocity vector across both axes. And what we're going to do is we're going to add them up. We're going to do vector addition, right? And we're going to get our final direction, a final vector with magnitude and direction. Okay. And here's the position vector. So the final position is going to be the initial position plus the initial velocity times time plus 1/2 at squared. If you take all the r's and these little r's on the top here, and just look at it in terms of total displacement. And this is kind of one of the equations we'll use a lot when it comes to, if I'm looking at the displacement function. So it's the total displacement is equal to the initial position. So the final position is equal to the initial position. That's what this means. Plus the initial velocity times time and 1/2 at squared, or P naught plus V naught T plus 1/2 at squared. A lot of times we say it that way as well. All right. This is one of the most common and most, the equations that we'll be using, and we'll be mixing it around to get different components. If you look at R final and R initial, that is the displacement, the change in distance. And a lot of times we can replace these with another formula. Okay. So here's an example of the kinematic equations represented graphically, right? So you can see that again, I have two vectors. I have V initial, right? And then here's V final. And you can see that the acceleration over time is, we kind of show it as the resultant vector, the one that kind of matches up, adds up to V initial to get the V final, right? Which makes sense, right? Because we have this initial velocity, and then we add some acceleration, and we get some final velocity. That's what's basically happening here, which is an interesting way to look at things, because a lot of times we don't see how acceleration and velocity kind of connect to each other. I know you guys aren't interested, but for the most part, people aren't interested in that kind of stuff. But for me, it's interesting because you see the relationship from a graphing perspective. Again, here's something that we can see. There's relationships here, the final position, if you will. So you have the initial position, you have some kind of velocity over time, right? Then you have some kind of acceleration, right? Until you get the final position, which is, again, interesting, right? So you have some initial position, but you have something that you speed up, you change your location, you displace yourself at a certain rate of speed, right? And then you can even use this other part to get to the final position at the end, right? So this is how that equation we just saw matches up graphically. And you can see it's just one vector adding to another vector, adding to a third vector until you get the final. Okay. So I talked about this. I'm not going to talk about it anymore. And again, we're going to really talk about more of this idea of two-dimensional movement being, we're going to decompose or decouple the X and Y components a lot more in this time. And we'll see more of that in Newtonian physics, which we'll handle or start talking about next week. So what the heck is a projectile anyway? And again, any object which is projected by some means, it's given some kind of energy, right? I've imparted energy to it somehow, and continues to move due to its own inertia, which is relative to mass, right? And again, the only active force from a projectile is gravity. So it's not something where the projectile itself has, some kind of propellant fuel that's going to make it go forward. That would be more like rocket science. And we'll talk about that a little bit. The reason why rocket science is so difficult, people say like, hey, I'm not a rocket scientist, right? And people don't understand what that means. But think about this, right? Imagine trying to calculate your total distance at the same time that your mass keeps changing. Your mass continuously changes over time, right? So why is that? Because I got fuel in the beginning, and then it's propellant. It's pushing me forward. And then as the propellant keeps going out of the rocket, so too does the mass keep going down, which increases the velocity of the rocket, right? But there's going to come a time where you don't know where it's going to be because it's consistently reducing, right? So that's why rocket science can be so challenging, especially if you add direction and gravity and a bunch of other factors, right?
Like math.
Was that?
We
Sorry?
figured out math like 2,000 years ago. We're good.
If only. If only math was so
We
easy.
still haven't figured out whether all integers can be represented as the sum of two primes. So, and that seems like a pretty simple thing, but no, we still don't know.
Off topic, but yes, you're right. Let's continue. The only active force is gravity. So here's an example of a football player. He's kicking a football, and notice that the perfect, nice, symmetrical motion of the ball, right? As it goes up and down. Now, this is assuming that the football is kicked right at ground level. Notice that this is kind of a misrepresentation of what really is happening, right? And it depends on how high the football player kicks the ball, right? Where the ball might go a certain distance in height. You can see this is a perfect parabola, right? And that is the shape that we're looking at right now. It's symmetric because the force that we impart on the y direction, it's going to be countered by gravity, right? But the force across the x-axis is constant. Let's think about that. So if I give if I have a gun, right?
Oh no.
In Fallout 76, right? And I'm firing a bullet. I'm joking. I'm firing a bullet from a gun, and I have a certain muzzle velocity, which is kind of a spec for a gun. So the bullet leaves the gun right at that particular velocity. It's going to slow, right? Even all bullets will slow. They'll lose energy, right? And they'll tend to arc downwards. Okay, typically. Now, in a very close range, just like in a video game, that's why they use rays or ray casting to kind of do first-person shooters in a video game. You won't see much of a drop in from a bullet, but if it's very far away, if you're I don't know, if you're snipering or something, in a video game, not in real world, then you'll see that there might be if it's a true video game that's got some good simulation to it, it'll drop the actual bullet will drop a little bit because of the distance, right?
I mean, if you play Arma, it's like crazy impossible to hit stuff at that distance.
It's the farther it is, the more factors there are. There's wind, there's your breathing and all kinds of stuff, right?
There are people who are good at it.
There are people who are good at it. So if you look at this is a nice representation. It's linear and it goes kind of up and down. There's two directions. There's components on the x-axis this way and components on the y-axis this way, and that's why it looks the way it does. Okay, so again, we got this free fall acceleration, and it's constant over the range of motion, and also the x direction, the x component is also constant, right? The one thing that changes is the vertical acceleration the combined vertical acceleration is not constant, right? Because I might have some vertical component, but it's being decreased by gravity so that it looks like it's not constant, right? And that's what gives us that parabolic arc. So again, if you look at these components, this is a great picture of how this works. So you have some, you see that the velocity vector across the y-axis, right, initially is quite large, and then it goes smaller and smaller until it hits this area of equilibrium. Equilibrium means balance, right, for those people who forgot. And then it starts increasing in the downwards direction because gravity has taken over. But meanwhile, take a look at the x component. The x component is absolutely the same every single place. Now, this is a simulation. In reality, you're going to have some forces that are coming at you, especially if the projectile that you're casting away from the origin is not the right shape, right? Cut through, the air resistance. Bullets are shaped properly. That's what they're made for. But what about a cannonball? Cannonball will have some resistance, especially even though it's very, very heavy. It's going to have some resistance to the air. There's going to be some crosswind effect. Actually, it'll affect bullets too, especially the farther they go. And here's something to always not do. Don't fire a bullet straight up, you ever do those 21 gun salutes? They always fire this way. They don't, like at an angle, they don't fire up here like this. There's a reason for that. Because one goes up, comes back down, and you don't want to be hit by a stray bullet in the head, right?
Yeah, I mean, if it goes far enough and up, it has enough time to accelerate going down, but it might be coming down at like terminal velocity.
Can still hurt.
Yeah.
Right. All right, so so we have the first type of motion I want to describe. So these are really key, guys. All right, so when I say, just like the equations that I had last time, there's going to be certain things you're going to see over and over again. So this slide here, so slide 24 on this page, I recommend you note it because we're going to see this thing. We're going to come back to it again, okay? So in order this guy is at the top of the cliff. There's this situation number one, which you're going to get in a problem, okay? So now we're talking about problems already, all right? The person is, firing a projectile vertically off a cliff, okay? But this is the first time of motion. And if you look at it, it comes off a cliff horizontally, and it's, and the histogram of what's going to happen. So when you do this, I'm just firing straight off, right? And what's happening is you have some height of the cliff, and then you have a distance or displacement that's r that's traveled. We use these equations. So equation number one would be, the distance in y, in the y direction, right, is equal to the initial velocity times time plus 1/2 at squared. We saw that earlier. Notice that there isn't an initial position because the position is at 0, right, at the origin. Because for the origin is where on top of the cliff, that's the y component. Notice we're decoupling the y component here from the x component. The x component, though, if I want to find just the x component alone, so not the total y component at all, but just the x component, it's just vxt. So the original velocity across the x-axis over time, like we saw, right? So that's interesting. We have these two components, and they're fighting against each other. So given enough time, if I had no gravity, or for example, if I was on a very high hill, or it would keep going forward, right? All things being equal, no air resistance and so on, okay? So that's interesting to note these two equations, how they work together. So we have these two equations, equation one and equation two. All right, so here's still the first type of projectile motion. We know that the acceleration is 0, right, on the x-axis, because we have a constant velocity. Constant velocity, remember when we take the derivative of velocity to get acceleration, we get a 0 if we have a constant velocity, right? And we know that's on the x-axis. We know on the y-axis, though, that we're going to get this negative acceleration, which is equivalent to the gravity, force of gravity, which is negative 9.8 meters per second squared. And we're putting a negative to it because, again, just to remind you guys, down is negative and up is positive in this particular case. So we have this other equation. We can say that the velocity across the y-axis final is equal to the velocity across the y-axis initial plus AT. Okay, that's also applicable here, right? And the reason why we're saying we're putting the equation in different forms, right, is because sometimes we'll need one form or another to solve the problem, right? We may need multiple versions of the same equation in order for us to solve a system of linear equations, which we do a lot more in physics than we did in calculus, all right? One thing we know is at the top, the velocity of y initial at the top is always 0, right? So that means that if I'm just throwing a stone down, this is the example of us just dropping a stone from the top of a building with some horizontal x component, right? But there's no real y component. I'm not throwing it up. I'm just tossing it down, okay? So I'm tossing the stone down from the top of a building, right? When I toss a stone down, I do apologize for that. I toss a stone down from the top of the building, then there's an arc that goes down, but I don't have a countering velocity on the y-axis up. I haven't thrown it up. I'm just tossing it down. So when I do that, I can also say that if I want to find the total velocity of an object, right, of a projectile, I can take the square root of the x component, velocity on the x side, and the square of the x component from a velocity perspective, and the square of the y component, and then we take the square root of all that, and we get the total velocity. For this. Why do we want to see these ones? If you notice, these ones are in different forms. This one has no t component. There's no time component at all. So if we don't have time and we want to find the total velocity, a lot of times we can find it just by subbing in this equation. Okay, so first type of motion. I'm on the top of a hill. I drop something. And here's an example of that in terms of a cannon. So a cannon is not firing any; it's firing at a 0, degree angle. So it's not. There's no angle at all for the cannon. It fires off, and you can see that the velocity on the x-axis. I can't repeat this enough because people get this wrong all the time. The velocity across the x-axis is always the same, right? So you notice the velocity on the x-axis is 20 meters per second, right? Meanwhile, the velocity on the y-axis is -10, -20, -30, and it keeps on accelerating because of gravity until we have some point in time when the particle hits the ground. Now, this is dependent on the height of the hill. The taller the hill, the longer it takes for the object to hit the ground. That's just logical, right? And then we can figure that out with our equations. Any questions around this basic motion? This is the first type of motion you're going to see in problems, right? On your test. Okay, so we talked about this. And what we want to try and do a lot of times, and this we'll do in lab, is I'll put together two sides of the equation. And this is where we're going to start writing things a little differently. We're going to have the horizontal component on one side and the vertical components on the other side. Yes?
I assume we're not dealing with air.
No, we won't be dealing with air resistance throughout. Pretty much, right? Because it doesn't make any sense for us. If you want to add forces to your game, you can to make it more interesting or whatever, some kind of resistance. But for the most part, we won't be talking about it. There might be a question or two that says you get this air resistance, and usually it's in terms of it could be negative acceleration. It'll be termed like this. You'll get air resistance in the form of on the x component with a negative acceleration of 0.2 meters per second, right? That's a consistent air resistance, right? That's what you'll get. You won't get like air resistance for the first part is this much, and then you're going to get a crosswind that's too much, right? And you won't need to do the sum of all forces too many times in this course. Okay, so again, let me just go back to the first example. So we have an object in free fall will accelerate with gravity, and then if we decouple this particular case, this is the example 1. To figure out where the ball will travel, we look at the horizontal and vertical motion separately. So if I'm just dropping an object in free fall, it's literally just gravity, right? So where I have, here's the vector. I have 0 across the x-axis, and across the y-axis, we have a negative 9.8 meters per second, right? So that's the vector, right, that I have, right? So if I was going to just drop the ball on the horizontal axis, it'd be just 0, right? On the vertical axis, I would have negative 9.8 times t, right? So depending on if I looked at the gravity, right, and I was just looking at consistent gravity like that, it would just keep on increasing or incrementing across the vertical axis here. Okay. Okay, here's example number 2. A ball rolls off a table with a speed of 3.2 meters per second. Okay, the table is 1.5 meters tall. When does the ball hit the ground? How do we figure this one out? Can we have a consensus, some discussion around this? It's very simple. Well, let's think about this. And here's the other question you might get. How far away from the edge of the table is the ball when it reaches the ground? Okay, so these are typical equations. This is for the first type of projectile motion. So I have an initial x component of 3.2 meters per second. Okay, so that's the first, we write down the pieces that we know. So on the x component, it rolls off a table with 3.2 meters per second. The table is flat, so there isn't any angle, right, to this thing for it to move. It just literally rolls flat off the table, right? 3.2 meters per second is quite quick, right? The table is 1.5 meters from the ground. So there's a relation to how far it can travel before it hits the ground, okay? What's going to drive it to the ground? Gravity, the y component, right? And it's going to be consistent. If I had no gravity, if I was in microgravity in space, and if I flicked the ball at 3.2 meters per second, it would just keep going, right? And that's one of the problems in space they always talk about, right? These micro punctures of super micro meteorites or things like that in space that can puncture right through your spacesuit, and it can happen at any time randomly, right? Like dust traveling through you, kind of thing. It's always a danger, apparently. So anyway, so you have this ball that's moving 3.2 meters per second. The table is 1.5 meters tall. When does the ball hit the ground? How do we figure that out? Let's just think about this for a second. It's traveling at 9.8 meters per second squared, right? So we know that it's 1/2 AT squared. That's the speed that it's falling. What's A in this case? Gravity, right? 1/2 AT squared, negative 1/2 AT squared, right? So I know that that is the force of gravity that's moving. I have no other vertical connection, right? So it's just going to drop. And if you look at the previous equations, let's just go back up to these. The first equations that we just talked about here, this is it. The total distance across the y-axis fallen, right? We know what the total distance is, 1.5 meters, because the height of the table is only 1.5 meters tall. That's a pretty high table, by the way. 1.5 meters is like up here, right? So, you know, you got to figure that it's falling. The initial velocity across the y-axis is 0 in this case, right? So we don't have to care about this part because there is no initial velocity up or down, right? We're not tossing the ball down somehow from the table, and we're not launching it up in any direction, okay? All we care about is 1/2 AT squared. So we know that the total distance is going to be 1.5 meters, right? We want to find the total time, right? So we got to position this function in terms of time, right? So if this is 1.5 and this is 1/2, I multiply both sides by 2 to get rid of the 1/2. So now it's 3 times AT squared, right? If you think about this. And then we'll do this in lab again. And then what I want to do is divide by A, the acceleration on the other side, right? So 3 divided by 9.8 meters per second is the total time squared. All right, so let's think about that. So 3, let's bring this up. So I'll do calculator. If I take 3 divided by 9.8, right, is equal to 0.306, and that's meters per, or let's say seconds. And I want to find the square root of that because it's t squared that I've got on the other side. So the total time it takes is 0.55 seconds, half a second for it to fall down, okay? 0.55, just keep that in mind. How do I know that? Because when I go back down, these are the things I've been given, right? I've been given that it's 1.5 meters from the table is 1.5 meters tall, and I don't care what this is. It says when does the ball hit the ground in time. When I say when, it's time. 0.55 seconds is when the ball hits the ground. We don't know how far it's gone yet. We just know that it's 0.55 seconds. Okay, now that we know it's 0.55 seconds, we can take that time and put it back into the x component. All right, so if I go back, and if you look at the x component equation, right, there is dxt. So I know that I'm traveling at 3.2, I think it is, meters per second, and 0.55 is the total time approximately. 3.2 times 0.55 is the total horizontal distance it's going to travel. So if I go back, so if I do calculator, so 0.55 times 3.2 is 1.76 meters. That's when the ball hits the ground. So when I flick the ball at the top of a table at 3.2 meters per second, it's going to take 0.55 seconds to hit the ground. That's the answer. And it's going to travel 1.76 meters away from the table. Does this make sense to you? This is the easiest type of motion you'll see. All right? There's no angle. All there is gravity, right? And we have 2 components that we'll write down again in lab. One component is on the horizontal, and the other component is on the vertical. Okay, so pretty simple, type of motion. Okay, here's the other question. It says, so how far away from the edge? What about the vertical speed? With what speed does the ball hit the floor? Now, this is more challenging. So I have the total distance, right? And I have 3.2 meters. What does this mean, speed? What does it mean? What does speed mean in this particular case? Did I say speed in the horizontal or speed in the vertical? No. We know the speed vertical. Speed vertical is 9.8 meters per second squared, right? On the negative, right? Because of acceleration, it's going to that's what's going to happen, right? But what's the total speed? How do we find this out? And this is where people get caught up, right? So we're looking at, so velocity final. So look at this equation number 3. Velocity final is equal to velocity initial plus AT, right? And this is only across the y-axis, right? So velocity final, right? If I was going to say what speed it's going to be, right? We know the speed this way, 3.2 meters per second. It's always going to be that speed, right? On the velocity on this side, and we can find out the total velocity in a second. So first we take a look at, to figure out this one, okay? So velocity initial on the vertical is 0. Remember, we start off the ball, we flick the ball from the top of the table. Initially the ball doesn't move, right? And then we add acceleration due to gravity and time. We know it's going to be 0.55 times 9.8, right? So again, if I was going to go to my nifty calculator, 0.55 times 9.8, approximately 5.39 meters per second is when it goes on the downward side. And then we have 3.2 meters across the x-axis. Okay, now we plug it into this final thing, right? Let me just bring that 5.39 squared times 5.39, right? So 29.0521. And then 3.2 squared, 29.0521. 3.2 times 3.2 plus 29.3921. Something like that.
How's it say to the right?
Sorry?
You can see on the right side of the calculator, 29.0521.
Do I have that somewhere?
Yeah.
Oh, yeah. 29.0521. I'll be okay. And then we have this total, 39.2921. And then we want to take the square root of that, which roughly works out to be, again, 6.27 meters per second. That makes sense? So the total velocity, again, we're going to have a direction, right? It's going down, pointing downwards, right? Because, by the way, I didn't multiply by, this would have been actually in a downward direction because I didn't put the, the right sign there, right? Because AT would be a negative AT, right? For this one, which would give us a negative velocity. All right. So again, we have we're moving towards the ground. So we're looking at 6.26 meters per second. That would be the final answer in that particular direction, right? Does that make sense? That's the magnitude of the velocity in a direction. Notice that here, the velocity, there is no vector in front of it, right? But I want you to think about it in terms of a vector anyway. Okay? Is all that make sense? Is anyone confused about what I just did? Why I used those 4 equations? I needed to for the question that was asked is the answer. Okay, let's continue with this one. Second type of projectile motion. So the first type was just dropping a stone off a height. This is the second type, where I have a football player kicking a ball, a cannon launching a cannonball from the ground. Okay. Notice there isn't any fall. So the ground, it's a symmetrical motion, right? That's what you have to look at. The ball can't continue falling below the ground in this particular case. It just falls to the ground. We don't care about how deep the ball goes into the ground because of the resistance or how much pressure it's exerting on the floor or anything like that. So again, we need to know the kicking angle, whatever the kick angle is, and whether it's the kicking angle or the angle of attack, if you will. So if I have an angle of attack where I put my cannon up, and I fire it off, there is a relationship with how high I put this. I change the angle to the distance that's traveled. Initial velocity, that's the muzzle velocity. So that's the velocity that the projectile leaves the cannon with. Okay, that's what I want you to think of it. Don't think about it inside the base of the cannon. All right, this is just at the edge of the cannon's velocity. In our case, for our simulation, it's when it leaves. Okay, that's the velocity when it's leaving. Just to be more specific. And now we're going to use trick. Now we're going to go back to week 1. Okay, remember, always remember. For the most part, you're going to have 2 components. You're going to have the X component and the Y component. And unless we modify or turn things around a little bit differently, which we will with Newtonian physics and so on, when we get out of particle physics. We always say that the velocity across the x-axis is v cos theta, and the velocity across the y-axis is v sine theta. So sine is related to the y component, and cos is related to the x component. This is key, guys. If I'm playing a video game and I want to know the next position that my ship will travel from a pixel perspective, right? If I sit at a particular point in time and I change directions anywhere on the board, right, on the game, right, and I'm kind of moving in a particular direction, and I want to know the next pixel that my ship will travel, I use this equation. Okay. If I want to fire a projectile in any direction in a 2D space in a video game, I use this equation, these two equations. All right. Usually we use radians on the computer, right? Here we're going to use angles, right, that are non-radian, right? But typically what we're going to use instead of degrees on a video game, we're going to use radians because that's what a lot of times our math functions require, okay? So what is the time required to go from A to B? So this basically tells us our two components. Well, what is the total time required? Well, we're going to have symmetrical motions. We're going to have a time where it comes up, and then it's going to come back down. So there's two sides of it, and they're completely equal, all things being the same, all right? That means like no air resistance and no crosswinds and anything else. All right, so we have, so those are two equations. So again, equations 6 and 7, which we're going to use alongside equation 8. So where the velocity final across the y-axis equal to velocity initial plus at. That looks very familiar. That looks like the last equation we used, right? And at the top, we know that the velocity of the y-axis is 0. So right at the top, every single time, if I said, how long does it take you to go from, the ground to the top? How long does it take? We can figure that out because of this symmetry. We know then that if that's true, that 0, right, is equal to v sine theta plus the force of gravity times time, right? We know that this is true because at the top is 0. So if you want to find, at the top, right, v sine theta then is equal to a negative, gt, right? And so we come up with the equation number 9, which is time is equal to v sine theta over gravity, right? So this is the time required to travel from A to C is 2 times of 9. So what we're looking at here, this equation right here, is the time it takes to go to the top, okay? And then there's a symmetrical time it takes to fall back down again, okay? So that's what we're looking at. So T then is 2v sine theta over gravity for the total time it takes for it to travel its total motion, okay? Why is that? And we're not even talking about, other factors at all. We're just, how long does it take to go from A to C? And again, if we go back to the pictures, here's A and here's C. If I go from A to B, right? From A to B, we're going to use this formula, from A to B, right? From A to C, we're going to use this formula, number 10. Okay, pretty straightforward. How can we find the maximum height between A and B? So A and B. Well, we know, again, that this is equation number 11. This is, so we kind of look at a couple of things, right? Where we look at the total distance, and we also look at on the y component, and as well as the acceleration on the y component. We know that y final, v squared final over is equal v squared initial plus 2a y on dy. This is the total, this is the maximum height. Or if we know that vy is 0, right? So for when it comes to the height, we can sub in that number 0 on this. This is the v final, and we can figure out that h, the total height, is equal to v squared sine theta squared over 2g. Okay, there was a question that I had from one of the students. What's the difference between sine theta squared and sine squared theta? Is there a difference? Yes.
Presuming that in the first one you don't have brackets, then in the first one you're squaring theta, the input, and then passing it into sine. Whereas the other one, you're taking sine theta, and then taking that whole thing and squaring it. So the output of sine theta, you're squaring it.
So the answer is,
No. I mean, yes, there's a difference. No, they're not the same thing.
Amar?
Between sine theta squared and sine squared theta.
Mm.
So sine squared theta is you take sine theta and square it,
Mm-hmm.
and sine theta squared is you square theta and sine.
That's more of a better one. So sine squared theta, you take sine theta and square it, and sine theta squared, if the theta squared was inside the brackets, right? Then is you take theta squared and then take the sine of that, right? So which one is this one? Is it sine squared theta or sine theta squared? Sine squared theta, right? So you're taking sine theta and squaring it, right? Yes.
I always found that superscript notation on functions confusing because when you put -1, it doesn't mean the same thing as when you put 2.
Yes, but let's continue. We'll talk about that afterwards. So v squared. So if I look at this, right? If I know my velocity squared, as an example, and again, think about this: velocity where? Velocity across the y-axis, obviously, right? And then sine theta squared, right? We're just trying to find the height, right? Over 2g, and there's no time component in here whatsoever. If you notice, this is a good one if you have no time component. Okay, so 2 times gravity as opposed to gravity squared or something like that. Okay, let's get back to find this out. And normally we talk about the height, and then we also talk about the range. Okay, range is how far away from the origin or the total displacement. That's why we used R earlier in our slides, where R is range. The total range is velocity across the x-axis times time, right? And then if we use 6, we can see that depending on the angle. So velocity across the x-axis, this part right here, we take that and multiply it by cos theta, right? Again, the angle of attack is what I like to think about, right? The angle of attack. Because the higher up the angle is, right, then the less energy is going to that component. And I like to think about it as in terms of energies, okay? So I got 2 energies. I got the energy across the x-axis, and I got energy across the y-axis to form my total energy in a particular direction vector, all right? So the more energy I put to the y component, right, as an example, and if I put less energy to the x component, it's going to be at a different angle, a much sharper angle, a much higher angle than if I put more energy on the x component and less energy on the y component. If the y component was only here, and there's a lot more energy on the x component, that means that my angle is going to be much closer to the ground, right? So when you think of it that way, sometimes it helps me anyway when I think about problems to understand the distance. So when I look at the total range in this particular case, I've got a couple of other equations. We already know that the time from A to C is 2v sine theta over g. We know that, right? So we know that we want to find the total range, right? And here what they've done is they've just rearranged the equation. Notice all we've done is move things around. So 2v sine theta over g, and then we take a look at v cos theta, right? V cos theta being this part right here, right? Which is the x component. And we know that then range can be written as v squared 2 sine theta cos theta over g, or v squared sine 2 theta. This is interesting because sine theta cos theta is, or 2 sine theta cos theta from a trig perspective is equal to, or let's not say equal to, it's the same as saying sine 2 theta. So we can use either one or the other to find our answers. So why am I mentioning these things? Because we want to put as many of these kinds of variations in the way we've written these equations to help you solve your problems. Yes?
When you say that we usually say negative meter growth scale.
Correct.
So in this case, should we take out the negative?
I don't believe so. No, I don't think so. Because again, what you're looking at is you want to find, this is the total time, right? So total time is being subbed in. Notice we have v cos theta times time, right? And then we know the total time that's going to take in terms of gravity, right? So we take this whole thing and sub it in for time to get this. That's what we're getting here, okay? Once we've got this, and again, this maybe is not written properly. Maybe it should be written like this, right? in terms of the equations, right? Because what I want to really take is I want to take one equation and sub it in for t, right? I'm just going to do that because it's going to offset my PowerPoint. But you understand what the point is. Then all they're doing then is just moving things around, right? So it's something over g. We know it's something over g. They're moving things around so that we have two, v's. We collect the v's, so there's v and v, it becomes v squared. And then we take 2 cos theta sine theta, which we can make it look like this with trigonometric identities. All right, but gravity in this particular case would be negative, right? I believe. We'll take a look at that again. Okay, and that's the total displacement across the range from the origin based on the initial velocity across the x-axis, right? And one thing that's missing from this one is the velocity x, right? Notice that this is the velocity x, right? This should be the velocity x, vx cos theta, right? Times t. That's what this should be. Okay. And okay, no, next slide. Next slide. Here we go. So that's the second type of motion. So the second type of motion is symmetrical motion. Okay, now this one. What do we know about the first one? The first one is we just drop a ball. The second one is we have a symmetrical motion. Now this is a combination of both, right? That's why it's shown last, right, so far as the third type of motion. So we have this symmetrical part, which ends about here, not drawn great, but it ends about right here. And then we have this other part where the ball is falling this way. However, there is an initial velocity at this point, right? The initial velocity going up is equal to the initial velocity coming down. We know that from Galileo's previous work in 1D motion, right? So if I throw, or I have an initial velocity in a particular angle, it's going to be the same velocity coming down at that particular angle, the opposite angle as it comes down, right? And so we have an initial velocity in this case. And then it's going to drop down. So we want to find that we need to know the total height. We probably need to know the total range. We probably need to know the total height of, on the y-axis, right? Away from the initial height, right? And we need to know how far it would fall. We also need to, a bunch of different things. So this is more complex than the other ones. Okay, so let's take a look here. We can use 2 different ways to get the answer. So here's the first way. Way 1, the total distance is v initial on the y-axis, all right, or actually v initial on both axes, plus 1/2 at squared. Okay, so that's the first way. And if you look at it, the v final, we can say that the total distance is the y final, which is the total distance across the y-axis, right? Sorry. The total distance is y final minus y initial, where we just decompose this into 2 parts. There's the y component, and this is the x component, okay? Let me take that back. This is the y component. I'll be okay, right? So we have the y final minus y initial, right? And then it's equal to the initial velocity across the y-axis times time plus 1/2 gt squared, right? And then when you move this around, you say that the y final, right? We know that y final is equal to 0, right? Is y initial plus velocity of y initial times t plus 1/2 gt squared. All right, so that's where we start off with. We start off with this equation. And then after some work, we can see that the total time, and a lot of times we want to use this quadratic formula. I tried to talk about this last semester, last part of last section, where I said that it's important for us to do this. But one thing to note with time is that there is no negative time, right? So when we want to try to find the total time calculated for how long it's going to take for something to reach a particular point, we only care about positive time, because we don't care about time in this direction. So something that happened before we launched our projectile, we don't care about that. All we care about is positive time. So we want to try and make sure that the answer for time is positive. So only one of these possibilities, when it's plus or minus, is going to give us a positive result. And so we ignore the negative result. And sometimes we don't know which one it's going to be. We don't know if it's plus or we don't know if it's minus. All right. A lot of times it's plus, right? Because when you add something, chances are, especially if it's a small number, you're going to get a pretty good answer that it's positive. But however, it depends on A. If A, the acceleration is negative, then sometimes that will make it so that when you add something to B, it becomes negative, right? A lot of times we want to use the plus sign, not the negative sign. So that's how we figure the total time. So this is the way we would find the for the time it takes for the ball to hit the ground from A to C. That's what we want to find, the total time. So if we know that, then we can sub in the total time. So again, here's we can solve for time in this particular case. Where y final, we know y final is 0, right? And then once we know y final is 0, we know that equations take the form of a squared plus b squared, a squared plus bx plus c. That's the quadratic formula. Ax squared plus bx plus c, right? Where a is 1/2 g, that's the a component. B is this vyi, which is velocity across the y-axis initial. And c is y initial. That's your constant, all right? So if you take these three things, so this part, from here on, oops, this part here, this part, oh, I can't do it without the t, and then just this alone, that's going to, you plug those three things into the quadratic equation, right, to get ourselves t. That's the one way of doing it. The other way of doing it is to find the time of the object to hit the ground, the time to get from A to B. We know that it's equal to, for time, notice it says this is our notation, time from A to B is v sine theta over g, right? We know that from a previous equation. And we know that the height, a total height is v squared sine theta squared over 2g. We also know that the total y, right, is 1/2 at squared, total y, right? So the total height from B to C is, again, you notice that there's this height, capital H, and this height, lowercase h, height of the hill, plus the total height that's happening right here, right? So that's the total height from B to C. So B to C, right? Because you have to add all this height plus all this height, right? And then once you have those, that's y max. So the total height that you're going up from a projectile plus the total height of the hill, that's y max. And so the total time between B and C, so between B, so A, B, and C, for between B and C is equal to the square root of 2 y max over g. And then the total time from A to C, from here to here, is equal to the time from A to B plus the time from B to C. So time from A to B, time from B to C, okay? And once you've broken up your equation that way, where you have, here's one part of it and here's the other part of it, you just add them both together to get the total. So if we know that, so we know that we add them together. Okay, now to find the range, the total range, how far it goes away, we know that we have Vxt is the total range. This is from previous equations. And then now we have to add in our angle. So where we just can't say Vxt anymore. We have to say V cos theta t, okay? Using the last two formulas. Where Vx is a constant, so all points Vx are the same. Remember? It's not going to change. The velocity across the x component always going to remain the same until it hits the ground, okay? So we can say that Vy final is equal to V sine theta plus GT. That's from equation 8, right? And once you've got that, you can sub in total V. Remember that Vx squared plus Vy squared, right? You can take the velocity across the y component and the velocity across the x component and sub them in until you get theta, which is the arc tangent of Vy over Vx. And actually, a lot of times we use this. So we want to find the total angle. This is right from trig again, right? We take the velocity across the y-axis and the velocity across the x-axis. So this is the final velocity we're talking about, because we're looking at final velocities here, right? To get a ratio, a gradient, if you will, of y over x, rise over run, right? And then we take the arctan, and you could actually put that in your calculator as arctan or atan. I think it's atan 2, if I'm not wrong, for some programs as well, right? atan 2. And there's a difference between atan and atan 2, by the way. Gives you slight differences, right? Then you get the angle that you're looking for. So that's how you get the angle. But you're looking for the range, right? So once you've got the angle, then you plug in the values for Vx and Vy and make sure that the values are positive. This is important. So going back to what I was asked earlier, you want to make sure the values are positive, right? And then you can find out the total range. Okay, we're going to go over this again in lab. I know it's kind of hard the way I've laid out the slides, but I wanted to make sure that those three situations are the ones that you're going to see in problems, okay? So today, by the way, I've released lab 3, all right? Lab 3. That's your practice for this week, is to do the examples that are on the back of this slide deck. So please make sure you get to them. I've released them for the entire week, so you don't have to wait till your lab to start them, although you could work on them during lab and ask questions.
And is it still bonus like the other ones?
Yep. If you do them, they're bonus. You don't have to do them, but I believe it's helpful for you to go through the problems. There's going to be some PowerPoints, I believe, I'm not sure if it's next week or the week after, where I don't have example questions that are part of the PowerPoint. I may, for that particular lab, have a separate PDF that has a bunch of questions. I may do that, all right? And there'll probably be like 3 or 4. Nothing too crazy, because these take a lot longer to do properly with a lot of the answers than it does for some of the things we did in last section, which we talked about limits, derivatives, and integrals, although some of the integrals took a long time. All right, so we know we want to find the acceleration at the highest point. The vertical velocity is 0 at the top. We know that, right? Vertical velocity is 0. And then the acceleration is not 0 anywhere along the trajectory of the projectile, because we know that we have gravity throughout the entire time, right? But there's going to be a point in time where there's going to be an equilibrium where the bullet is going to hang for like a fraction of a second in space, right? Where it's not going up, it's not going down. So again, we have this initial velocity on the x-axis.
Bullets, Wile E. Coyote movement.
Right. The velocity on the x-axis initial is equal to VI, so velocity initial on the times cos theta, and velocity y initial is equal to velocity initial on times on the y-axis sine theta, right? So that's what it looks like to be. Now notice it says VI, right? And then same thing here, VI. What does that mean? What component is that? That's the muzzle velocity. So to draw it out, okay, if I was going to draw this out, so I mean that if I have some kind of muzzle velocity this way, right, as an example, and I have my axes here like this, there's one axis, and I have another axis that looks like this. Let's see if I can do this without any kind of weird stuff, right? Yeah, I can't believe I just got that done. So I'm going to have a number written at the end here, which is the muzzle velocity, right? So for example, let's say 100 meters per second. I have a cannon that fires a cannonball at 100 meters per second, and I have some kind of angle of attack. Let's say the angle of attack is 45 degrees, okay? So what is the Vx component? So the velocity across the x-axis. I take 100 meters per second, multiply it by cos theta, cos of 45. What is that? So if I go cos of, calculator, okay, 45 degrees. This is using degrees, not radians. So cos of 45 is 0.707, right? So 0.7 times 100 is about 70.7 meters per second across the x-axis. Remember that amount is never going to change, right? It's always going to be 70 meters per second across the x-axis. And across the y-axis, right? Again, it's 45 sine theta, right? So again, it's 0.707. It's almost like it's matched. That's a weird relationship. 0.7 one way and 0.7 the other way. Well, of course it makes sense, right? What magic triangle is that? It's a 1, 1, root 2 triangle, yeah? Right? 1, 1, so it's the same proportions on both the x and the y, and root 2 across the hypotenuse, right? So where the x and y components are x this way, and y, so if I was going to draw them out here, I would say this is the x component from here to here, let's say, and then here's the y component from here to here. These would be 1, 1, and this would be root 2 in terms of our relationship. So if it's 0.707, it'd be 70 meters per second across the x-axis, and 70 meters per second across the y-axis to give us 100 meters per second across the total vector. The magnitude of the vector would be 100 meters per second, right? So what I've done is kind of decoupled, right, the total velocity for this particular vector across both the x and y-axis. So we know that the x direction in this particular case has a constant velocity, so therefore acceleration across the x-axis is 0. Constant velocity, when you take the derivative of velocity to get to acceleration, and if it's constant, it's 0. So there is no acceleration across the x-axis. Whereas the acceleration across the y-axis is always negative g, right? Because as we move forward, you know, we have an initial velocity. We're gonna subtract gravity from it every frame, and that's why we use this funky equation where we have the initial position plus the initial velocity times t plus 1/2 gt squared. And like we said, it looks like this is what it looks like. Notice that there's a little vector that we can draw downwards like this. When we draw them out, we have the initial velocity times time, and then we add 1/2 gt squared, which looks like this, to get the final velocity vector, right? Here's the final distance vector, if you will, actually. There's the relationship between the final position, right? And the initial velocity and the acceleration component. So these are the three terms that we talked about. And then you get some number x and y for the final position. All right, so again, we can say that if we analyze stuff that we've talked about already, the range of the maximum height of a projectile, right? So here we have some velocity initial, and we have some angle theta, right? And we have some height h with a range r, right? And now we're analyzing it more mathematically, where we know that Vy at this particular point A is equal to 0 because the velocity is not positive or negative across the y component at this particular point in time. Again, just a little bit of reviewing it from another perspective. So the maximum height of the projectile then would be where height is v squared initial, sine squared theta, theta initial, whatever the initial angle was, over 2g. Okay, and again, this equation is only valid for symmetric motion. What does that mean? Because sometimes you have, imagine if I said, well, okay, I have my bullet fired, and then I have a weird bullet. It's not a regular bullet, where, you know, I fire a bullet, and then it's a rocket-propelled bullet at the top, right? So it comes up, and there's some kind of rocket-propelled bullet that makes it go, gives another increase of velocity across both the x and y axis. I don't know. That's kind of a weird thing. You kind of fire the bullet off, so it's in the air, and then poof, it takes off as a rocket. I've never seen a kind of bullet like that, but let's just suppose, right? Non-symmetric motion or something else that would make it less symmetrical for whatever reason. Maybe some of its mass came away, right? So maybe there's a two-stage bullet. You fire it up, and as soon as it fires off, there's two bullets that go two different directions, right? That would be non-symmetrical because one part of its flight would have a certain mass, and the other part would have half the mass, maybe different directions, right? So that would be non-symmetric motion. All right, the range of a projectile then can be expressed in terms of the initial velocity vector. So whatever my velocity initial is, by the way, both components, x and y here, right? Squared sine 2 theta initial over gravity, right? And you can see that you've got this situation where you have different angles and different distances. Notice that the higher the angle as it approaches 90 degrees, right? What is the distance traveled when the angle is 90 degrees? 0, because it goes up and comes straight back down, right on top of your head, right? Which we don't want the bullet to happen. We don't want that situation, bullet hitting you. 75 degrees is a bad angle because the range would be a lot more severely limited, right? What about if the angle is greater than 90 degrees? The projectile is firing behind you, okay? If it's greater than 90 degrees. If it's firing 90, it's above you. If it's firing at 75, it's kind of tilted away from you a little bit, right? There's 60, and then what's the greatest angle that it can go to? The best angle is 45 degrees. So if you want the greatest distance, the greatest range, always angle your stuff at 45 degrees in terms of total velocity. If it's lower than 45 degrees, it's going to be shorter, right? Because notice that if I go to, there's some similar angles. So 75 degrees and 15 degrees, doesn't matter whether it's 15 or 75, the distance is going to be the same because of the way the amount of energy you're putting to whether the X component or the Y component again, right? And the same thing goes with 30 and 60. 30 and 60, that's the complementary angle. Why? They both add up to 90 degrees, right? So 75 and 15 add up to 90, 60 and 30 add up to 90, but look at 45. 45 seems to be the best angle to fire something if you want the maximum range. So this is really good for a strategy game, right? If you ever play a strategy game and if you're actually using real angles, like you're actually trying to calculate what's the best angle to fire a bullet and you have a slingshot or something, 45 degrees, right? It'll be the farthest you can get it. But what about if we're going to have problems sometimes where the problem says the object is X number of distance away from you, right? So we have a range. What is the correct angle to attack something? This goes back to the ancient Greeks and Romans when they had, and even before that with the Chinese, where they had different kinds of catapults. Actually, if I'm not wrong, I don't know if it's the Greeks that stole from the Chinese. Can't remember. But originally there was this, you had these catapults, and the catapults would try and hit a particular point in space, right? And they were far away. Now, subtracting air resistance and all that kind of stuff, you had a distance, and there would be calculations made to figure out what's the angle of attack, right? With a specific velocity, a muzzle velocity. Now remember, these are catapults. Is the muzzle velocity of a catapult consistent? What do you think? Consistent. What's on a catapult? What are we catapulting? Not a cow, rocks, right? And this is where, professional armies in the past, what they would do is they would shave the boulder down so it's the exact same shape as much as possible. Why? Because if they don't shave it down, it's an unknown quantity. Unknown quantity, I don't know how far it's going to travel with the same elevation, right? So if I increase the elevation, right, as an example of a bullet, I want to know how far it's going to travel based on my calculations, right? So they try and get equal sized rocks. Try it. You ever, primitive man didn't know how to shave things down 100%, right? Or it was close, but not 100%. There's also the mechanisms. The mechanisms weren't exactly perfect on the catapult. Some catapults are made better than others for different people, right? They were tested in the field, of course, ahead of time when they had time to do that. But you had some variation because of wind speed, variation because of materials, variation because of the bullet, right? In our case, everything is perfect, right? The catapult is exactly the same every single time. There's no wind speed, there's no air resistance, and the bullet is perfectly shaped, all right, to get us where it's supposed to go. Okay, but this is a very interesting way of looking at things. And if you see here, they've actually given us an example of the initial velocity. The initial velocity here is 50 meters per second, all right? So they've given us approximate distances based on the initial velocity being 50 meters per second, okay? With the formula that the total range is initial position times initial velocity times t plus 1/2 at squared, yes?
It can the measure because of the ideal branching and hitting angle. So we increase the amount of rate, and it tells that 25 to 35, the angle is the most probability of the hitting performance rather than 45.
Well, you'll see that if you go 25 to 30 degrees, the thing with it is it's low to the ground, right? If it's closer up, you have more of a chance of line of sight. Problem with a higher angle is you don't know where the thing is going to land, right? You can't really, it's kind of weird, right? It's the same angle that you're using. The complementary angle of 75 is, like I said, is 15 degrees. You can see something that's lined up properly, right? Once it becomes, kind of way up in the sky kind of thing, right? It's hard for you to calculate the angle, but there's some mortars and there's some other kinds of non-direct fire weapons that we use. Anyone play Warhammer? Warhammer 40K, right? Okay, I'm the only one. Anyways, I know it's expensive. Anyways, if you ever look at that, they have these mortars. There's direct fire weapons like bullets and guns, and there's non-direct fire weapons, indirect fire weapons, where you have this angle of attack, right? And in my mind, I always think about, okay, it's going to just, kind of go over fortifications and so on. But we always think about these things hitting 100% of the time, kind of thing. But the reality is it's much more, there's more calculations involved. All right, so again, the maximum range occurs at 45 degrees, as you can see that. Complementary angles will produce the same kind of distance. One thing they talk about in this PowerPoint a lot, this is right from the book that I've been using, is these 3 ways of, and we talked about this not last week, but a week before. We talked about these 3 ways of slicing down a problem, and I recommend it. So conceptualize it, categorize it, and analyze it, right? Where you want to conceptualize what it looks like, get all the information, all that kind of stuff. You want to categorize it. What kind of problem is it? Is it type 1, type 2, or type 3? As an example, which type of problem is it? And then analyze it, put everything in, all the equations to solve the problem. Okay, and then finalize it. So here's your non-symmetric projectile motion, right? Non-symmetric projectile motion is the one where it's not going to be ending here. That's type 3. That's the type 3 motion. So there's 3 types, right? Symmetric motion. Type 1 is when you drop something, right? Non-symmetric motion, but you're dropping it. Symmetric motion when you're kicking a ball, right? That's type 2. Type 3 is this non-symmetric motion when you're kind of sending it off a 45-meter tall building, right? So non-symmetric motion. All right. So we want to try and break the y direction into different parts, right? So we have this part from here to here, and then with this part from here all the way down to the ground, right? Okay. Another topic that we cover in motion in 2 directions is something called uniform circular motion, all right? Uniform circular motion, where I have some kind of motion around an axis of rotation, okay? So I can imagine that I have some kind of axis of rotation, and where the magnitude of the displacement is constant, right? Let's just say. So I have something like a Ferris wheel, and we're going to talk about that. And it's the same, or maybe I have a sling, okay, like old slingers. Again, I'm military slingers, right? Where they have a slingshot, and that's not a slingshot like we think about now, where we have some kind of slingshot with a rubber band. We're not talking about that kind of slingshot. We're talking about the old ways of putting a sling bullet inside something and then spinning it around your head, and then what you do is release, right? You build up centripetal force until it gets the maximum you can muster, and then you let it go, right? And when you do that, it produces more force than if you were to throw it at somebody with your hand. And why is that? Well, actually, science fiction movies use it all the time, the slingshot effect, right? Let's slingshot around the sun and we'll increase our speed until we get to a greater velocity than we can normally do. So it's kind of the same thing when it comes to circular motion. And we're talking uniform circular motion, not circular motion that changes or has a changing radius or something like that. So again, the change in the velocity vector is due to the change in direction, and the direction is going to continuously change as the projectile moves around the center of mass, if you will, or the center of wherever your bullet's tied to. So we have this notion of centripetal acceleration. That's what it's called, right? Centripetal acceleration. And the acceleration is always perpendicular to the path of the motion, right? So we talk about velocity, but then centripetal acceleration. So where is that happening? The acceleration always points towards the center of the circle of motion. So again, going back to that slinger idea, I have kind of a slingshot I've got over my head. I keep doing this. Where's the acceleration towards? The center, towards my hand. That's where the acceleration happens, right? The acceleration is always perpendicular to the velocity. So we can say that acceleration c, AC, the centripetal acceleration, is equal to my velocity squared over the radius. All right? This is a kind of a key formula again when it comes to circular motion, which we're going to see in other places as well. Okay? V squared over R. Okay, period. What does that mean? The time required for one complete revolution. Yeah, that's what it is. So how long does it take for me to just to make the stone go around one time, right? And it's the speed of the particle be the circumference of the circle of motion divided by the period. So 2 pi r, all right? So that's the circumference of the circle. How long is my sling bullet sheath, if you will, right? How long is this thing that I'm holding? And then over the total velocity, how fast can I make this go, right? And that's the total time or the period that it takes to travel along that path. Okay. A few more slides, guys. I know I'm going a little longer than normal. I try and end off like an hour and a half, so I won't tire the crap out of you guys, but please bear with me, right? We have also something called tangential acceleration. Now that is can be hard to pronounce. Try that, 5 times fast. Tangential acceleration. So it's kind of a tangential, and then it's like acceleration right afterwards, right? Where we have this acceleration on the tangent. So what's the tangential acceleration as opposed to the centripetal acceleration? Centripetal acceleration always points towards the center of where things are turning, right? And tangential happens across as a tangent to that type of acceleration, or the motion, right? So here, the tangential acceleration is across the, it's perpendicular, or sorry, it's a tangent to the centripetal acceleration, which goes towards the center. Right, so this is tangential. And then we have, if we take both these two components, we can get the total acceleration, which is the direction of the vector that where the vector is moving towards, as an example. So in this particular case, you can see that if the tangential acceleration is moving this way, and then the centripetal acceleration is moving this way, you can see that the total acceleration is moving in this direction. We can again use Pythagoras for this to help us, where c squared is equal to a squared plus b squared. And as you can see, we have these two things. Tangential acceleration causes the change in the speed of the particle, and the radial acceleration comes from a change in the direction of the velocity vector. All right? So why are we talking about this? Because when we want to find tangential acceleration, we take the absolute value of the change in velocity over the change in time. Whereas the radial acceleration, the acceleration around, right, is the acceleration, the centripetal acceleration, the negative component of the centripetal acceleration, which is equal to negative v squared over r, right? And then the total acceleration, we get magnitude, and we also get direction. And we can say that acceleration, like we said before, think about acceleration as c squared. So c squared is equal to a squared plus b squared, where c is equal to the square root of a squared plus b squared from Pythagoras. We want to get the total acceleration, which is different than the radial acceleration, the centripetal acceleration, right? Or the tangential acceleration. Whew, all kinds of accelerations, right? By the way, there will be a cheat sheet for the final test. I will give you a cheat sheet to work with, right? A lot of you did change the cheat sheet dramatically from the one I gave you. For the most part, it worked, whatever you did, because the average on the test is pretty good. Okay, I'm going to talk about relative velocity, but we're not going to have questions too much around this, right? Because once we go into relative anything, we start talking about relativity in some ways, a short version of relativity, right? But I want you to think about it. I'm going to mention it here, but I'm going to skip these slides. This is for you to read, right? I'm not going to have questions like this in the test. I want you to think about relative velocity as a velocity based on a particular frame of reference, right? If I'm inside the frame, and I'm not talking about frames, computer frames, I'm talking about like your point of view, right? If I'm inside the frame of reference, for example, the frame of reference of the Earth, do we feel the velocity of the Earth as it travels around the sun? Because we're inside of the frame, right? Our viewpoint is so locked into our little world that we can't feel there's no feeling of acceleration. But actually, our Earth is accelerating, or there's a velocity around the sun, And
I think the Earth is accelerating, I think, fairly close.
it's the velocity is, so there's a velocity around the sun, and there's also the sun that's moving around its point of the galaxy, right? And the galaxy is moving around the universe, right? So we have a bunch of velocity. And if you add all those things up, this is where teleportation becomes really challenging to think about, right? Because I got to think about where the Earth is going to be, right? The next second from a global coordinate system perspective. Global meaning the galactic coordination map, where if you think about this galactic coordinate system, where our world is going to be, the next second is going to be vastly different to where it was a second ago, right? Because of velocity, right? So this is where we come to think about teleportation. Someone who can really teleport. I was asked last week, if I can make anything, what would I make? I'd make a teleporter, right? Why not? It'll be life changing, right? But it's really impossible in our current physics and current understanding for many reasons. But this is one of them. Let's say we could tackle, actually scanning somebody to the subatomic level, let's just say, without killing them somehow, right? And let's just say somehow we could, like Star Trek says, scatter their atoms across the universe and put them back together again as a regular person. How the heck would where would we send this person? Because we'd have to figure, it'd be harder than rocket science, because we'd have to figure exactly where they're going to be in the next second from a global galactic coordinate system perspective, or maybe universal coordinate system, way out there, global versus local. Our local coordinate frame is on the Earth, right? And then we can talk about the next step up, where our Earth is parented to the sun's motion. And I'm using parenting, just think about this in terms of making a unity game, right? I got the Earth's motion, I got the sun's motion, the Earth's running around the sun. The Earth is parented to the sun. The sun is parented to the galaxy is parented to the universe. The universe, who knows, right? But you can see that there's a parent-child relationship, and that parent-child relationship gives us our coordinate frames, right? As well as, what about our clothes? Our clothes are parented to us and other things. We keep going down the line at the subatomic level. So when we talk relative velocity, it's from a coordinate frame. We have an observer. As an example, he observes, a person moving a certain rate of speed, but it's relative to his position in his observation. So I'm not going to go over this. It's interesting things to think about, but I'm not going to ask you questions around it. I just want to mention it because it's part of kinematics and motion, all right? So we're just going to skip this part. First subscript, second subscript, we're not going to go there. 67. And it talks about calculating accelerations. And now we're down to the last part. So this is test one. I'm going to talk about it after I stop. Any questions with things we've talked about today? So we've talked about motion in two directions and three different cases, right? Where you drop something, a particle, or you launch a particle from the top of from a flat surface, or when you launch a particle up from a height of some kind. Those are the three possibilities you're going to run into for the most part. Three different kinds of cases. And then we also talked about circular motion with different kinds of acceleration that we're going to be kind of talking about later. So in lab, I'm going to try and work out the problems with you, so I can give you those bonus marks for free. So if you follow along with me in lab today, Wednesday and Friday, then it's pretty simple to get your bonus marks. I'm going to try and work all those problems out with you. Okay. All right. Let me just stop this recording then, and we'll move on to our test results, and then I'll let you guys go.